In C, the amount of memory a program can use is decided at compile time for static and automatic variables. However, many problem-solving tasks need a data size that is not known until the program runs. For example, reading an unknown number of integers from the user, constructing a graph where the number of vertices depends on input, or allocating a buffer for a file whose length varies. Dynamic memory allocation lets a program request memory from the operating system while it is executing, just like renting a storage unit only when you actually need it. This flexibility prevents waste, such as allocating a huge static array that is mostly empty, and enables handling of arbitrarily large inputs, limited only by available RAM. The function prototype is void star malloc with a size parameter of type size t. Size is the number of bytes needed. Malloc asks the heap for a contiguous block of at least that many bytes, and returns a pointer of type void star that can be cast to any data type pointer. If the request can be satisfied, a block is reserved, its content is indeterminate, meaning it contains whatever was previously in memory, and a non-null pointer is returned. If the request cannot be satisfied, null is returned. Size calculation often uses the size of operator. Int star p equals malloc of n times size of star p, where n is the number of elements. This expression is mathematically size equals n times size of int. Using size of star p instead of size of int makes the code resilient to type changes. Void star calloc open parenthesis size t n mem comma size t size close parenthesis semicolon takes two arguments: the number of elements n mem and the size of each element size. The total requested bytes are n mem times size. The key difference from malloc is that calloc 0 initializes the whole block, guaranteeing that every byte is 0. This is useful when you need a clean slate, such as allocating an array of counters that must start at 0. Internally, calloc may compute the product and then call malloc followed by memset, but the standard guarantees the zeroing. Example, char star buff equals calloc open parenthesis 10 comma size of star buff close parenthesis, 10 bytes, all set to \0. The 0 initialization adds a tiny overhead compared to malloc, but it removes the need for an explicit loop or memset after allocation. Void star realloc open parenthesis void star ptr comma size t new size close parenthesis semicolon changes the size of a previously allocated block pointed to by ptr. Three cases exist. 1. If ptr is null, realloc behaves exactly like malloc open parenthesis new size close parenthesis. 2. If new size is 0 and ptr is not null, the call is equivalent to free open parenthesis ptr close parenthesis and returns null. 3. Otherwise, the implementation tries to extend the block in place. If that is impossible, it allocates a new block of new size, copies the old data up to the lesser of old and new sizes, frees the old block, and returns a pointer to the new location. A typical usage pattern is growing an array. Int a equals malloc open parenthesis capacity times size of a close parenthesis semicolon, while open parenthesis need more close parenthesis open brace capacity, multiplied by equals 2 semicolon, a equals realloc open parenthesis, a comma capacity times size of a close parenthesis semicolon close brace. It is crucial to assign the result to a temporary pointer, first to avoid losing the original block if realloc fails. Free of void pointer ptr returns a previously allocated block to the heap. After a successful free, the pointer ptr becomes a dangling pointer. It still holds the address, but the memory is no longer owned by the program. Using a dangling pointer leads to undefined behavior. The safe practice is to set the pointer to null immediately after freeing. Free p equals null. A double free occurs when free is called on a pointer that has already been freed or on a non-heap address. Double free can corrupt the heap metadata and crash the program. By resetting the pointer to null, a subsequent free becomes a no operation because free null is defined to do nothing. Both malloc, calloc, and realloc return null when the system cannot satisfy the request. Good code must always test the return pointer before using it. Int star p equals malloc n times size of star p. If p equals null, then pair malloc failed and exit failure. The global variable urino is set to n memory on most systems. which can be inspected with parer or strarer. In competitive programming, programs often terminate on a null return because the judge provides ample memory. But in production code, you must handle the failure gracefully, possibly by cleaning up and reporting the error to the user. Malloc 01 simple pointer bump, small header often 8 to 16 bytes per block. No, contents indeterminate. Calloc O of n for zeroing where n equals total bytes, same header as malloc, yes, all bytes set to 0. Realloc O1 if block can be extended in place, otherwise O of k where k equals the minimum of old size and new size for copy, may allocate a new block plus old header until old block freed. No, the new part of an enlarged block is indeterminate. The overhead is the bookkeeping information the allocator stores, size, and flags. Calloc adds a linear pass to write zeros, which can be noticeable for very large allocations. Realloc may trigger a copy, making it slower than a fresh malloc when many resizes happen. Allocating enough space up front or using exponential growth reduces the number of copies. Int I equals malloc 5 times size of a for int I equals 0, I less than 5. Increment I equals I plus 1. A equals realloc at 8 times size of a for int I equals 5, I less than 8. Increment I equals I plus 1, free A. After realloc, the first 5 elements remain unchanged 1 to 5. The new 3 elements are set by the loop to 6, 7, 8. So the final array is 1, 2, 3, 4, 5, 6, 7, 8. A variation may ask what happens if realloc returns null. The correct answer is that the original block is still valid and must be freed, and using the return pointer without checking leads to undefined behavior. Another common trace, freeing a pointer twice or accessing memory after free, both of which are undefined and would be marked incorrect. These questions test understanding of pointer semantics, copy behavior of realloc, and the necessity of error checking. Checklist for safe dynamic memory use. Calculate size with sizeof, never hard code byte counts. Check the return value of malloc, calloc, realloc against null before dereferencing. Initialize memory if needed. Use calloc or memset right after allocation. Assign realloc result to a temporary pointer to avoid memory leaks on failure. Free every allocated block exactly once. After free, set the pointer to null. Avoid pointer arithmetic on freed memory. Treat the pointer as invalid once freed. Use tools such as valgrind, address sanitizer, or static analyzers to detect leaks and double free. Prefer exponential growth, for example double the capacity, when expanding arrays to keep the number of realloc calls logarithmic. Document ownership. Clearly state which module is responsible for freeing a pointer passed between functions. Handle allocation failures gracefully. Clean up already allocated resources, report the error, and exit or fallback.